We are almost at the end of the entire curriculum for college algebra and trigonometry. Today, we are going to focus on our section 8.6 and 8.7, which is radical equations and functions. There's 4 learning objectives for today. The first one being solving radical equations, the second one being evaluating a radical function, the third, finding the domain of a radical function, and then finally, our last one, being able to graph radical functions. So let's jump into it. First objective for today, solving radical equations. We have our formal definition of a radical equation, which is simply an equation in which a variable is in the radicand of a rational expression. So anytime you have an equation that involves an nth root, whether that root is cubic, whether it's to the fourth, fifth, sixth, or maybe it's just a square root, we're dealing with radical equations. And again, anytime you see the word equation, you're going to have an equal sign somewhere along the line. As usual, when solving these equations, what we do to one side of an equation, we must do to the other. We need to make sure that everything is balanced. And our objective when solving radical equations is simply getting that radical over to one side all alone, and then eventually reverse engineering that radical by either squaring both sides, taking the cube of both sides, whatever that index is, raising it to that power in order to eliminate that root. Okay. And finally, we have solving radical equations, or I should say root equations, that's the better wording for it, containing an even index by raising both sides to that power. That may introduce a solution that does not work when you plug it back in. And we've seen this before in earlier lessons, but we call these potential solutions an extraneous solution, one that we solve, but then when we plug back in, it's rejected. Okay, so we need to be on the lookout for these extraneous solutions. This next slide is just the step-by-step procedure in solving radical or root equations. Again, that first step, you really want to isolate that root on one side, and then you want to reverse engineer it to get rid of that root based off of what index we're talking about. Then we solve the new equation by isolating our variable. And then last but not least, we want to check the solutions to make sure both of them work, especially if we're dealing with an even index, because we might have to reject a solution. Let's jump into it, looking at our first example for today. So straight off the bat, let's get that square root all alone. We're going to go ahead and add 9 to both sides so that we're looking at the square root of 5n minus 4 is equal to 9. Now we're going to reverse engineer. The opposite of taking the square root is squaring. Whatever we do to one side, we must do to the next. When we take the square root of 5n minus 4 and we square it, that helps us get rid of that square root, and then 9 squared is 81. So now it's just like solving a regular equation with one variable. Combine some like terms, adding 4 to both sides. And then the opposite of multiplication is division, so we're going to divide both sides by 5 so that we get our final result to be n is equal to 17. Now, last but not least, let's check our work. When we plug in our 17, we have 5 times 17 gives you 85. 85 minus 4 gives you 81. The square root of 81 gives us 9. And 9 minus 9 gives us 0. So our solution works, and we're done. Again, if you feel like I'm going a little too fast, feel free to pause, and you can go back and rewind. Now let's look at a cubic root in our second example. Once again, we want to make sure that root is all alone. So we're going to go ahead and subtract 8 from both sides so that we're looking at the cube root of 5x plus 1 is equal to -4. Reverse engineer, so we're going to raise both sides to that index 3. So now it's going to be to the third power. That gets rid of that cubic root. So now we're just looking at 5x plus 1 on that left-hand side. And then -4 raised to the third is just, well, 4 times 4 is 16, and 16 times 4 is 64, but we can't forget about that negative. Gives us -64. Now it's back to solving a very straightforward equation. Let's combine some like terms. Subtract 1 from both sides. So we're looking at 5x is equal to -65. And then last but not least, let's divide both sides by 5. So our final value is x is equal to -13. Let's go ahead off to the side here, check to make sure that solution does indeed work. So we have the cube root of 5 times -13 plus 1 plus 8. Does this equal to 5? Well, 5 times -13 gives us -65. And -65 plus 1 gives you -64. The cube root of -64 gives us -4. And -4 plus 8 gives us a +4. So what do we get? We get that the solution does work. And we're good to go. Let's move on to example 3. Again, our objective first is to get that root all by itself. So what I'm going to do is I'm going to first subtract 2x from both sides, and then I'm going to add the square root of 2 minus x to both sides. So when we do that, we end up with the square root of 2 minus x on that left-hand side is equal to 1 minus 2x. Reverse engineer, we're going to square both sides. So 2 minus x on that left-hand side. The right-hand side, we're going to have to use our FOIL skills. And when we do, we get 1 minus 2x minus 2x plus 4x squared. And then we can do some combining like terms. -2x plus a -2x is just a -4x. we can combine some more like terms. We can add x to both sides. And then let's also combine our constants. Let's subtract 2 from both sides as well. So we're essentially looking at 0 is equal to, and I'll put it into descending order. So 4x squared comes first, minus 3x minus 1. Would you look at that? We have a quadratic function that we're dealing with. Can we factor this? Well, let's see if we can utilize our AC method. Four times -1 gives you a -4. And then our b is -3. What are factor pairs of -4 that add to -3? That's just -4 and +1. So we can break this up into, we keep our 4x squared the same. Then we have a minus 4x. We have a plus 1x to give us that -3x. I'll color code so you could really see how we manipulate this. And then we keep our last term exactly the same as well. Now we'll utilize our knowledge of factor by grouping. So that those first 2 terms we can factor out of 4x so that we're left with x minus 1. Those last 2 terms we can factor out a 1 so that we're left with x minus 1. We did this correctly. You'll notice that inside the parentheses, it's exactly the same. So we can pull that x minus 1 out from each of those terms. And when we do, we're left with a 4x plus 1 in those other parentheses. Don't forget that this is all equal to 0. Because our goal is to find our potential values of x. So now we can separate, we can set x minus 1 equal to 0, and then we can set 4x plus 1 equal to 0. One potential answer is x is equal to 1. And then another potential answer is x is equal to -1/4. Okay. Last but not least, we want to check to see if these work. So we want to plug these back into 2x is equal to 1 minus square root of 2 minus x. Right? If we plug 1 back in, we have 2 times 1 gives us 2 equals 1 minus, in parentheses, 2 minus 1. And 2 minus 1 is 1. The square root of 1 is 1. 1 minus 1 gives you 0, not 2. So 2 does not equal 0, which means we need to reject x is equal to 1. It's not a solution. This is known as an extraneous solution. Let's try -1/4. 2 times -1/4 gives you -2/4, also known as -1/2. And then we have 2 minus -1/4. It's the same as 2 plus 1/4. 2 plus 1/4, well, 2 as a fraction is 8/4. And so 8/4 plus 1/4 gives you 9/4. But we want to take the square root of that. So the square root of 9/4 is the same as the square root of 9 divided by the square root of 4, which is 3/2. So we have 1 minus 3/2, and 1 as a fraction is 2/2. So 2 over 2 minus 3 over 2, that gives us 2 minus 3 is negative 1. That gives us negative 1/2. And that's what we had on that left-hand side. Negative 1/2 is indeed equal to negative 1/2. So x equals negative 1/4 is indeed a solution. This is our only solution. Right? Our second objective, we have some more definitions. Radical functions is just a function that's defined by a radical expression. So in order to evaluate a radical function, we find our value of f of x for that given value of x, just as we've done multiple times throughout this course already. It's sort of like a plug and chug. So for example 4, we're given this function and we just want to evaluate it when our x is 5. And then we want to evaluate it again when our x is negative 2. Which means wherever you see an x, you're going to go ahead and draw some parentheses. And then inside those parentheses, you're going to fill it in with that value of 5. And then we'll solve. 2 times 5 gives you 10. 10 minus 1 is 9. Square root of 9 gives you 3. So final result is 3. Now, again, you want to keep in mind that potential solution of being negative 3. And so technically our solution could be plus or minus 3. But in most cases, at least at this level in mathematics, we tend to favor the positive 3 a little bit more. But it's good to note. I'll put a little side note. Square root of 9 could technically be plus or minus 3. All right, part B. Now, wherever you see an x in this scenario, we are going to draw parentheses and then fill those parentheses in with the negative 2. 2 times negative 2 is negative 4. Negative 4 minus 1 gives you a negative 5. And you'll notice that this is no longer a real solution. It ends up being imaginary. This can be broken up into the square root of 5 times the square root of negative 1. And we know the square root of negative 1 is I. So our final result is the square root of 5i. You could also write no real solution here if you wanted to be a little less specific. So I'll write as a side note, no real solution. Only imaginary. And then once again, you can also, have that plus or minus. So third objective for today is being able to find the domain of a radical function. And so this is really important, especially when you look at like the indexes for the functions or for the um, expressions that are presented to us. If we have an odd index, then we don't have to worry about a negative being in the radicand, whereas if it's an even index, we do. Because if it's an even index, automatically we're no longer in the real number system. That root is not a real number, so we enter into the imaginary world. And so we have restrictions involved. Something to just be mindful of. Uh, and then another thing that you want to think about when finding domains is if you're dealing with a fraction, you want to make sure that 0 never appears in that denominator because that makes the value of that fraction undefined, which is once again not possible. So, domain of radical functions, this is to sum up what I just said verbally. But when the index is even, the radicand must be greater than or equal to 0 because we cannot have negative values that will lead to imaginary numbers, which is not part of the real number system. However, when the radical is of odd index, then we're good to go. We have no restrictions in that case. Let's now jump into example 5, where we're asked to find the domain of this function. F of x is equal to the square root of 3x minus 4. So we have no fraction here, which means we don't have to worry about undefined values in the denominator. But we do have an even root, right? In disguise, square root, there's a little 2 here. Normally never put it there, but it's good to know it's even when there's no number represented, which means that underneath our radicand, this has to be greater than or equal to 0. Okay. Well, what values make that possible? Let's solve this inequality. Go ahead and add 4 to both sides. And then last but not least, we'll go ahead and divide both sides by 3. So our domain is simply all values that are greater than or equal to 4/3. This is an inequality form. They ask us to put it into interval notation. So how does this look on a number line? We draw out our 4/3. It's going to be a closed circle because we're including that 4/3, and it's all numbers greater than that. So interval notation, hard bracket, 4/3 shoots up to positive infinity. And we're done. Easy enough. But let's do some more examples together. Now let's try cubic function. Cubic functions, easy, especially when there's no fraction, so we don't have to worry about it being undefined in the denominator. We have no restrictions here. Which means, what is our domain? Our domain, simply all real numbers. I'll write it in English. I was going to give you the all real numbers symbol, which is just this, but we do need to put it into interval notation, which is just negative infinity to positive infinity. And we are done. You want to get a question like this. Odd index questions takes 2 seconds to solve. All right, let's move on to our 4th objective for today. which is being able to graph radical functions. Before we graph any radical function, we first must find the domain of the function to really see where our graph is going to go. And it's also important to just keep in mind your toolkit functions, also known as your parent functions, knowing, oh, okay, what does the square root of x look like? The shape of it, at least, right? What does the x squared look like? Or our famous y is equal to x, or x cubed. And then from there, you can do your transformations based off of the other functions that they give you. So we have the function f of x is equal to the square root of x. This is an even index. Domain must be greater than or equal to 0. So we're looking at our only values of x could be from 0 to infinity. Hence, when we do sketch this out, we get this function or this visual. Another thing that can help you out if you forget all of that, just create a table. Choose good values of x, plug it into your function, get your y points, and then physically just plot those points and figure out where your graph takes you. Okay, and that's what they say down here. Make your table. Making tables for like quartic functions or quartic roots or cubic functions, cubic roots, is really beneficial as well. Okay, so I sort of visualized it with my little laser tool on the previous slide, but our famous graph of f of x equals the square root of x looks like this. And we have a nice, beautiful table off to the side here. Right, let's graph our f of x is equal to the square root of x plus 3. So again, our parent function is our whole square root of x. And you know that the square root of x, maybe I'll put this up here, it's just going to look something like this. That plus 3 tells us that we're going to have a horizontal shift 3 units to the left. So 1, 2, 3, that's going to be our new starting point, and then it's going to go off like that. But I'll create the table and everything so you can really see that as well. What's our domain in this case? Well, our domain is moved a little bit because of that plus 3, right? Underneath the radicand can be greater than or equal to 0. So when we subtract 3 from both sides, we get our domain is just x is greater than or equal to -3, which is -3 up to positive infinity in interval notation. Right, that's our part A. Now our part B, we did graph already, but let's create the table to just verify that this graph is indeed correct. When our x is -3, we have y is 0. Good. When our x is, let's pick some good numbers. When our x is -2, -2 plus 3 is 1. Square root of 1 is 1. So -2 and then 1. We'll make this be 1. Good. When x is 1, we have 1 plus 3, square root of 4 is 2. So 1, make this 2. And then when x is 2, we have 2 plus 3 square root of 5, which is a little higher than 2. And this is just slowly increasing. Beautiful. So we did that well. Now finally, let's analyze what our range is, all of our possible y values based off of the graph. We know it'll never go below. So our range is simply 0, and then it shoots up to infinity. And then you're done. Now let's look at example 8. We have this cubic function, our cube root of x. First step, just find the domain. It's an odd index. So our domain, we have no restrictions. We have all real numbers in interval notation. That's just negative infinity to positive infinity. Part B asks us to graph. So let's create a nice, beautiful table off to the side. Choose some good values of x that we can plug into our function to create our y or calculate our y. So I would say, why don't we choose maybe -8? Let's choose -1. Let's choose 0. Let's choose +1. And let's choose +8. Cube root of -8 gives you -2. Cube root of -1 gives you -1. Cube root of 0 is 0. Cube root of 1 is 1. And cube root of 8 is 2. And so now let's plot these. 3, 4, 5, 6, 7, 8. That's -8. -1, 0, 1, 2, 6, 7, 8, 1. And then our y's. Okay. So we have -8, comma, -2. We have -1, comma, -1. I'm gonna put my -1 in the wrong spot. We have our 0, 0. We have our 1, 1. And we have our 2, 8. So you'll notice it'll look something like this. Always want to draw in and label your function. I don't think I did that on the previous example, so I'll go back and do that in a moment. There. Beautiful. And then last but not least, now let's use this graph to find our range. Notice that we have no restrictions for our possible y values. So we once again have all real numbers, which in interval notation is just negative infinity to positive infinity. And we're done. That was the last example for our section 8.6 and 8.7. These are some great additional problems from our workbook to really enforce your knowledge and understanding of this unit. Highly, highly recommend. But let me know if you have any questions beyond this. And I hope this was helpful. Take care.